How's it going, everyone? All right, we're back. So logistics, homework 5 is due today, but you probably have some late days, so you can just sort of keep using those forever. We have the final project proposals were due on Tuesday. If you haven't turned one in, do it. And I posted the Kaggle competition on bird classification if you want to do that, sort of in lieu of coming up with your own final project, basically. And so now that all of the homeworks are done, you should be working on your projects and doing that kind of stuff. Any questions about, yes? Soon, hopefully today. I've gone through a decent number of them, and I'll just sort of keep going through them. But yeah, any other random questions? Cool. You guys had Ali last time. How did that go? Good? Okay. He had like 2 slides, and the recording thing didn't get his audio. Did he just like not know about the mic or something? Did he just kind of yell at you guys? So I couldn't hear anything that he said, and he doesn't have very many slides, so I have no idea what he talked about, but I'm just going to pretend like I know. So let's talk about what you guys talked about last time. So we talked about this problem of gradient explosion or vanishing, where with really deep networks, basically the gradient information, the stuff that's actually sort of modifying the weights and doing the learning, can sort of fade by the time you backpropagate all the way through all of these layers. This is especially sort of problematic with saturating activation functions. We have gradients that vanish because at some point it probably will get multiplied by like a 0 somewhere. With non-saturating activation functions, or with sort of these large weights, we can get really big gradients as we're backpropagating. So this kind of means like we're screwed either way, right? We either have saturating activations or non-saturating activations, and we're probably going to fall into one of these categories, and we're going to have unstable learning if we have these really big models. So when we sort of scale up to a bunch of layers, our learning, it doesn't really go anywhere. And this is especially problematic with these large networks because the first layers are the ones doing really important stuff like line and edge detection and stuff, but we're never going to get any gradient back to them, so they're never going to learn to do any of that. So we'll never sort of have any really meaningful gradient in the whole network because we never really start modifying these early layers at all if we have sort of gradient vanishing stuff. And if you have gradient explosion, you just get nans right away and everything kind of blows up. So one way of dealing with this is this idea of batch normalization, which apart from kind of the original AlexNet paper, I would say batch normalization is like one of the biggest breakthroughs in terms of how we use neural networks, because we can now build these really deep networks and we can still sort of train them without really doing anything special, and it works really well. And the basic idea is we're just going to normalize the activation functions to have 0 mean, 1 variance, and we're normalizing them over like a batch, but also over spatially the responses from a single filter. And so this stabilizes learning the model because of some statistics and stuff. The idea basically is that at every layer you want to have outputs from that layer that don't really change that much over time. This is this idea of minimizing the internal covariate shift. So you don't want the outputs of layers to be very different from each other, and you also don't want them changing a lot over time while you're learning. And so doing this batch normalization sort of stabilizes that process and means that our learning is a lot more stable, so we can do some cool things like have really deep networks and also have really large learning rates, and it speeds up learning and makes it a little bit more stable and stuff, so that's cool. We also talked about, or I assume maybe you guys talked about, this is nice for the activation functions that we're sort of commonly using too, because we're kind of in this nonlinear domain. You can imagine that like if we have ReLU activation functions, but we're always in the positive domain going into those activation functions, it's really just linear, right? So you want something that sort of spans this gap of like sometimes it's going to be negative, but sometimes it's going to be positive. It also adds in basically this regularization because you're comparing every image to other images in the batch. So you never really like see the same version of the image. It's always kind of relative to the other things that the network is looking at in a given batch. And that's good because it's basically this other regularization parameter where we can't really overfit as much to like one particular image because we're never really going to see that particular image exactly the same way multiple times. And we talked about GoogleNet or InceptionNet, which was this new big architecture that uses batch normalization and gets higher accuracies. And then we talked about residual connections, which were another way of addressing this gradient vanishing problem, where if you want to basically make sure that some gradient is backpropagated all the way back to the input, what you can do is add in these residual connections, where going into sort of this residual block, we're going to basically feed the output of the previous layer up here into the next layers, but we're also going to take that and sort of route it around. And now we have this new function where instead of if these layers are sort of calculating f of x, the output of our residual block is going to be f of x plus x. So instead of modifying what x is, we're going to basically be changing x a little bit. So we still have our component of x in there, but then we're also adding in some like new amount of information based on whatever f of x calculates. And what this ends up doing is basically if you have a bunch of these strung together, like in this example where we have this really long residual network, all of these are basically identity functions as they go forward. And so when they go backward, they're also identity functions to whatever the gradient happens to be. So if you have some gradient all the way at the end here, it gets backpropagated all the way up through just a bunch of identity functions, basically. And you're basically ensuring that if you have some gradient at the end, you're going to backpropagate something up to the beginning. It might not be super particularly meaningful, but it ensures that you're going to get information back to the beginning and you don't suffer from sort of this gradient vanishing that we had earlier. Do people understand sort of batch normalization and residual stuff? And we talked about how we can get really deep models with this. I think there are like 1,000-layer models that people are playing around with on like MNIST and CFAR and stuff. On ImageNet, it's usually like on the order of hundreds or something. We also talked about basically the next step is if we're doing sort of these 3x3 convolutions, remember that each of these convolutional filters are looking through all of the channels. So every filter has basically some spatial component, but then is also looking through every channel in the input. And the idea is that basically maybe we don't need that to happen. Maybe a filter only really needs to look at a few channels in the output of the previous layer to do some meaningful computation. So we're going to do these group convolutions where instead of having the every filter look at every channel in the output of the previous layer and sort of the input feature map, we're going to split the feature map that's going into these groups, and you're going to run a convolution over just sort of this subset of channels. So you're still running it over the whole space of the feature map, but just running it on a few of the channels. And then you can sort of recombine all of those together at the end. Let me go over here and just fix my little thing. Happening next. And so just a quick example of this. Hopefully you guys went through this. But if we have this 3x3 convolutional layer, and the input is this 32x32 feature map with 256 channels, say we have 128 filters. If we do a grouped convolution, then we're going to split this feature map into 32 groups. So each of those groups is going to be 32x32x8 channels. Hopefully 8 times 32 equals 256. And then we have 128 filters that we're dividing into 32 groups. So on each of these 32x32x8 feature maps, we're going to run 4 filters. Those filters will be 3x3x8 channels. And then we're going to merge basically all of these channels back together at the end. And we're going to get some output, which is going to be basically the same size output if you hadn't done this grouped convolution. It's still going to be 32x32x128, but we have a lot less computation because these filters are only looking at a subset of the channels instead of all of the channels. And so building off of this, basically, you can replace these 3x3 blocks with these grouped convolutions, and these grouped convolutions can be much larger because they're computationally more efficient. And so we have ResNext, which is building off of the ResNet architecture, but replacing 3x3 convolutions with these grouped convolutions. And you can see that basically you replace, a 3x3 convolution with 64 filters with a 3x3 convolution with 128 filters, but you have this group size parameter, which in this case for most of these is 32. So the actual amount of computation either stays the same or actually, yeah, I think for this it's about the same. You can look at the number of floating point operations at the bottom. So the actual number of computations stays about the same, even though we're using a lot more filters because we're only running them on a subset of the channels. And this is cool because if we run more filters, maybe we'll extract more information, and that's good. And then we see that we have these one-by-one convolutions. And so if we just had a bunch of sort of grouped convolutions, all one after another, you would basically never get any mixing between different groups, between sort of these subsets of the channels. But if we have these one-by-one convolutions, they don't have this grouping parameter. So they're still looking at all of the channels in the input, and they kind of do this recombination between these different channels so that there's still some information basically flowing between all of the channels in your feature maps as you're going throughout the network. But at these 3x3 convolutions, which are the most expensive, we don't have to look at all of the channels. We're just looking at this subset. And so over time, basically, we've kind of inched upward and upward on ImageNet. The biggest sort of single jump was basically the original jump to using neural networks, and then sort of the jump right afterward, which basically was like, let's make these networks a lot bigger. And then we've kind of pushed further and further up on this. I think ResNext 101 is like close to being the best one. There's probably someone who's at like 81 top 5 accuracy right now or something. The other thing that people do is basically train a bunch of these models and run them all on an image and average them together. And with these ensembles, you get a little bit higher performance and stuff like that. But these are sort of just running a single model on a single image, the accuracies that we're looking at right now. And sorry, that's 80% top 1 accuracy, not 80% top 5 accuracy. And so we're sort of starting to saturate ImageNet, and we talked about, what are we doing other than image classification? Well, this other stuff, segmentation, detection, captioning, and that's what we're going to be talking about. So you talked about semantic segmentation, which is sort of densely labeling all of the pixels with the class that they're associated with. So all of the people are labeled with red, all of the cars are labeled with blue. I guess there are trees that are labeled with green, et cetera. And you talked about sort of an architecture for doing semantic segmentation, which was sort of this convolutional network, which, if you guys are paying attention, looks a lot like VGG16, and then followed up with basically this deconvolutional network that takes this output feature map and maps it back to sort of the size of the original image and predicts sort of these segmentation masks that predict sort of a separate channel for car and for dog and for person, et cetera. And so now we're going to talk about object detection, but we're not actually first. We're going to talk a little bit more about segmentation just to kind of finish up and talk about some different architectures that people use for segmentation. So one important concept is basically this idea of convolutions and deconvolutions. And you can think of a deconvolution as basically just being a convolution backwards. So a convolution is, you're taking some window of pixels from the input and doing some weighted sum to get some pixel in the output. A deconvolution, all you're doing is you're taking some input pixel and you're mapping it to the output and sort of blowing it up. So you would multiply this pixel by some weight and basically add it into whatever pixel might already be here in your output. So your output would start as a bunch of zeros, but you can see that basically this deconvolution operation, you're going to have overlapping predictions from the input. So you're going to be adding in basically new information at every spot you apply this deconvolution. So you apply it here, and you have some weight that maps to here, and so you add in some scaled amount of your input to this pixel, and also to this pixel, and this pixel, et cetera, for all of sort of the pixels in this output kind of region that you're mapping onto with this deconvolution operation. And deconvolutions are also how you do backpropagation in convolutional neural networks. So remember that, if our convolution is our forward operation, when we're backpropagating gradient, we have to basically go from the output to the input with what our deltas were, or what our sort of gradient is at that layer. And basically that process is doing a deconvolution. So we'll have some error associated with this pixel, and we basically have to map it back along the same weights from that filter to the input and figure out what the error is associated with at the input layer. And that same process is just a deconvolution. So these things are basically flipped versions of each other. And it's actually really easy to implement these deconvolutional layers if you already have a convolutional layer, because you already had to implement them for the convolutional layer anyway. It's just the gradient backpropagation step. So for semantic segmentation, we have this big network where we have this convolutional network and then this deconvolutional network, and we're predicting these masks. And we can basically think of this as like we have this encoding mechanism, which is taking our input and coming up with some output feature map that is like an encoding of this original scene that we have up here. And then we have this decoder network that is basically taking this feature map and using it to predict this output of what the actual segmentation masks are. And this is a really common sort of idea in computer vision that comes up again and again, which is sort of this encoder-decoder architecture. So this is an important thing to think about. One interesting thing is basically we have these really coarse features. So remember with this neural network, the whole point is that basically as we traverse through this network, we get more and more semantically meaningful information, and we're also sort of downsampling, so we get coarser and coarser features. So at the beginning, sort of in these layers, we're just doing a bunch of like edge and curve detection and stuff. So we have really fine-grained features up here, but they don't really have a lot of meaning to them. From a bunch of like edges, you can't really directly predict whether or not something is a dog or not. You have to kind of do some extra processing. And then in these intermediate layers, we get some combinations of the beginning features that might correspond to like curves or like sort of simple shapes. See a lot of like eyes and stuff come up in these intermediate layers. And then at the end layers, we start to get really semantically meaningful information where we have neurons that fire for like the head of a dog or like the legs of a person or just like a person in general, especially once we get down into sort of these last level of features. But these features are really coarse. Remember that sort of this network was originally designed just to predict like what class is in an image, not necessarily where all of the pixels were for that thing. So we have these two networks where we have this convolutional network that's encoding this really coarse features, and then we have this network whose job it is to sort of take those really coarse but really semantically meaningful features and turn them into this segmentation mask. And in particular, like these are one-by-one features. So this is just a vector down here. There's not actually really any spatial information that's kind of encoded into the structure of this. Now, since it's being trained to predict this mask, it will kind of turn some of these different pieces of this vector that it's predicting into sort of spatially meaningful concepts. But it has to kind of learn to do that on its own, which is really difficult for it, et cetera. And so we want to figure out basically a way from going from these really coarse features to these fine-grained predictions for like on each pixel, what is the class associated with that pixel. So one idea for doing this was this idea of UNet or Segnet, kind of both came up with it around the same time, of basically you have your encoder, which is sort of this network on the left-hand side, and it goes to this really semantically meaningful but very coarse-grained feature. And we also have our decoder, which is on the right-hand side, which takes these really coarse features and makes our sort of end prediction. Why don't we take some of the information from these intermediate feature maps and transfer them over to this decoder architecture as well? So to predict, which pixels are associated with a person or a dog, we have to like know what a person or a dog is and be able to find those things in the image. So we need these features sort of at the end that tell us, was this a person or was this a dog or a cat, et cetera. But we also want really fine-grained features from sort of these intermediate layers to tell exactly, how far does the person extend, what are sort of the borders of their arms or their head, et cetera. So the idea is basically you can either take these features from the intermediate layer of your encoder architecture and concatenate them on to the features in your decoder, or you can do this residual style where you would just add the features in to the features over here. So there are different ways of doing this. You can either do some kind of mapping or concatenation or residual connections, whatever. The point is basically just take some of these features from your encoder and transfer them over to the decoder. So, at this stage in your decoder, you have basically all of this really semantically meaningful information that came from the really deep layers of your encoder, but you also have information from the shallow layers of your encoder that have sort of fine-grained pixel information. And that's really important for doing semantic segmentation because you want to get all of these pixels exactly right. Another idea that people came up with for doing semantic segmentation was this idea of spatial pyramid pooling. And this is the idea basically that if you have sort of this CNN and this convolutional network and it produces this output feature map from your input, especially for sort of really large objects or really small objects, you may want to look at basically multiple different scales. And we saw this when we were looking at, when we were looking at other sort of machine learning techniques, especially for object detection and stuff. We looked at a bunch of different scales when we were trying to find objects in an image. And spatial pyramid pooling is doing sort of a similar thing. So if we want to process this feature map, one thing we might want to do is some kind of pooling on that, especially like average pooling or max pooling. And so what spatial pyramid pooling does is a bunch of different sizes of pooling to produce some output feature map that basically has a multi-scale representation of kind of this input feature map produced by the CNN. So we're going to do max pooling or average pooling or some kind of pooling here. But we're going to do it to different degrees, basically. So let me just count this quickly. I think this is like 6 by 6 or something. So maybe this is like a 12 by 12 output feature map. So one thing that you might want to do is do like 2 by 2 max pooling or 2 by 2 average pooling to get some slightly downsampled version. But you could also imagine doing sort of 4 by 4 pooling and get this 3 by 3 output feature map. You could also imagine doing sort of poolings of sort of successively larger sizes to get these different feature maps that correspond to basically looking at this input feature map, but with different, but at different scales, basically. And then we're going to run sort of a convolutional layer on each of these output pool of the pooling operation, sort of these output feature maps that are all at different scales, and we get some feature representation here that again is all at different scales, and then we're going to upsample these features that have all basically been processed looking at different scales of this input feature map. We're going to upsample them all so that they're all the same size and concatenate on sort of the original features. And the idea is basically that as we do this operation, we have sort of our original feature map, which was the output of this CNN. And before we've had, especially sort of here, we had this output as basically being this 1 by 1 by some number vector. But in reality, we're probably using like maybe a 14 by 14 feature map or something from earlier on. So if we have sort of some feature map here that has some dimension that might be like 14 by 14, we can imagine these pooling modules as basically looking at different scales of this feature map, doing some processing, and then resizing them all to be the same scale again. So when we run it through a decoder architecture, which would be some convolutional network, we get some final predictions where we're looking at the feature map here at a bunch of different scales, so we can process objects of different sizes and hopefully capture all of the information. So if you have like a really small person or a really large person, maybe the really small person would be represented in sort of this original feature map, and we could get that information just from sort of this original one. But maybe a really large person, it would be hard for a convolutional network to sort of recognize a large person in this really fine-grained feature map. So you would want to do some processing on some smaller version of that feature map And maybe, by doing this downsampling and processing on this smaller feature map, we can recognize these larger objects, and then some large objects would get kind of caught because of this multi-scale representation. So this spatial pyramid pooling you can include in sort of these segmentation architectures where we basically will have the same kind of thing here. We have an image and we run it through some convolutional layers. We have some feature map. We do spatial pyramid pooling, which takes care of basically looking at that feature map at different scales. And then we output some prediction for our segmentation mask, and we do some basically large upsizing operation to get back to our original size of the image to predict basically all of the pixels in this image. And finally, we have sort of putting a bunch of these concepts together. This was a Google paper, I think, DeepLabv version 3. So one thing you can imagine doing for this spatial pyramid pooling, instead of doing sort of max pooling or average pooling or something like that, you can also imagine basically doing convolutions, but making your convolution have a larger window or a smaller window sort of in the input. So these are called Atrous. I have no idea how to pronounce this. Atrous convolutions. And the idea is basically, before our convolution basically looked at this 3x3 window of pixels, and they were all right next to each other. But that isn't, sort of necessary for this convolution operation. All we're doing with a convolution is basically this weighted sum. So we can actually basically have this convolution where the input pixels are spaced out by some amount. So this would be, an Atrous convolution where the pixels were spaced out by 2 instead of 1. You could also imagine doing it by 3 or by 4, et cetera. Question? Yeah, so what this is going to do is basically replace the pooling operations in your spatial pyramid pooling. So if you want a pooling operation that downsamples by a factor, that's sort of looking at a larger window. So imagine you have average pooling that sort of averages out 2x2 windows or 4x4 windows. You can actually just replace that with this Atrous convolution, which will do a similar sort of operation where you're looking at these larger windows when you're making this output. And so the idea is basically instead of just doing pooling operation, there's some extra processing that happens with these convolutions, but also you're still doing this same idea where you're looking at basically the feature map, this feature map from your encoder. You're looking at it at different scales, basically. So an Atrous, like just a regular convolution, would basically look at it with no change in terms of scale. And an Atrous convolution with really widely spaced out inputs would be looking at it downsampled by a large factor, basically. And you can imagine that basically these Atrous convolutions are very similar to like if you took the feature map and just shrunk it and then ran a convolution on top of it. It would be doing sort of a similar operation, but you're not losing as much information because you're not actually explicitly doing this shrinking. You're actually still getting information from all of these input pixels. So people have been using these for a bunch of things where you want to kind of do this multi-scale processing of your feature map. So we have this same architecture where we have basically this encoder and decoder, where the encoder is kind of this stage of the pipeline, and your decoder is now a lot simpler than it was before. We're not doing a bunch of convolutional layers. Basically, we have this feature map that gets produced from spatial pyramid pooling. We're going to upsample it by a factor of 4, add in some fine-grained features, do some convolution here, and then upsample that prediction again by a factor of 4. All of these things are sort of tunable, so you can imagine putting in extra layers, at different phases in this pipeline, et cetera. But the idea is basically the same, where we have this encoder and this decoder. We basically want these really semantically meaningful predictions that come from the output of the encoder, but we also want basically some fine-grained features from our encoder to get sort of really pixel-accurate predictions. And the spatial pyramid pooling helps basically examine this feature map at a bunch of different scales, so we get predictions for objects that occur at different scales. And you'll also see kind of this technique a lot where you have some network that's basically supposed to process your input and come up with some kind of features for it. And the standard is basically you take that and you pre-train it on image classification, or you pre-train it on ImageNet, and then you add on some extra convolutional layers that do the actual thing that you care about, and you take this whole network and you fine-tune it on the task that you care about. So in this case, you fine-tune it on segmentation. But people do this for detection, for classification, for captioning, for any sort of large scale image processing that you want to do. Oftentimes it's hard to basically get enough training data to train a whole network from scratch, but ImageNet already exists. And so you can take sort of the feature extraction part of the network that you want to train, pre-train it on ImageNet, and then you already know that basically this network will produce pretty good features in sort of this output feature map. There'll be features that are very specifically tuned to like predicting different breeds of dog, and also like predicting all of the random categories that exist in ImageNet. But it turns out that it doesn't matter that much. You basically have some version of visually meaningful information in these features. And then when you plug it into some new layers that do the actual thing that you care about doing, once you start training this architecture basically end to end, it will do slight modifications to your encoder as well. And those modifications will shift these features a little bit. So instead of being good at predicting dogs, they're good at predicting what pixels are associated with a dog versus what pixels are associated with other things. So just some output images from DeepLabv3. We see that we have these are sort of like really good results. I like, this bird is cool because it gets the little feet of the bird, but it doesn't really predict pixels for this branch. So it has like these really sort of very fine-grained pixel level accurate predictions. This person is cool. It sort of has the arms and the foot sticking out to the side. And the bicycle is sort of labeled in green here as well. Some more random predictions. The fingers here are pretty cool that it sort of manages to label these really fine-grained things. Just like sort of pretty good semantic segmentation predictions, which is cool. Any questions about semantic segmentation? You guys sort of more or less understand what's going on, this encoder-decoder architecture, all these kind of little improvements that people make to it, stuff like that. Yeah. Yeah, well, if you want to basically do this thing where we're adding in like these fine-grained features here, that can take a bunch of different forms. A typical one is like you could have a one-by-one convolution on this feature map that goes in this direction, and then just add on sort of the output of that one-by-one convolution to whatever your feature map was here. You could also just concatenate the features. So if you have a 32 by 32 by 8 feature map coming in here, and this is a 32 by 32 by 16 feature map coming in here, you could just concatenate those two together and get a 32 by 32 by 24 feature map. I'm really bad at mental math. And so you can imagine just sort of mashing these two images together, or adding them together, doing kind of anything basically will get you some pretty good results. And it seems like in practice it doesn't actually really matter that much which version you choose. If you do concatenation, you end up with these really big feature maps a lot of times, or like they're twice as large as they would have been otherwise. If you do addition, you end up losing some information. So there's trade-offs both ways basically. Cool. So with semantic segmentation, we have this issue where this is one of the output segmentation masks for an image, and like these are all labeled with person, but like how many people are there in this image? It looks like approximately 5, I think. Maybe these are just arms in the background, but sort of they're all mashed together, and you can't really tell like these pixels right here, are they associated with this person or with this person? So one thing you might imagine doing with processing images is instead of like just figuring out which pixels are associated with what class, you might actually want to know sort of what the objects are in the scene and where they are. And so to start with, we're just going to be talking about object detection, which is basically this task of find all of the instances of a bunch of different objects in the scene, figure out where they are and what they are. So in this case, we're finding a bunch of cars and putting bounding boxes around those cars. We're also finding people. It finds this sort of traffic light in the background and maybe this handbag. And once we've performed object detection on an image, we can do some more interesting processing. You can see like how many different people are there in a scene, or how many different cars, or where these things are. And so we're starting to focus basically on instance level detection instead of basically labeling all of these pixels as being person and sort of leaving it at that. So we've already talked about object detection a little bit when we talked about deformable parts models. And remember that deformable parts models were this thing where we basically are training this SVM on top of hog features. We have our base filter, we have different parts filters, and we have some notion of where those parts are likely to be in an image. So we run basically the base feature, or the base detector over the hog features. We run the parts detectors over the hog features at twice the resolution. We get a bunch of responses from these filters. We transform those responses based on, if there's a head right here, then you know that the body of the person is actually a little bit below it. So we want to basically do some processing on these responses of these parts filters, combine them all together to basically figure out where there are high responses of both these root filters and these part filters. And at the end, we basically have some response map of where there might be a particular object. And so you can train these for people or for other objects too, things like bicycles, dogs, et cetera, and do this deformable parts model thing and get some predictions for what is going on in the image. And you're going to get basically some output here, and in particular, you're going to do some post-processing on this feature map to actually figure out what the boxes would be at. So this is, again, deformable parts models we're going to run at a bunch of different scales too. So we're going to run this at the original image, but then we're going to shrink it a little bit and shrink it a little bit and shrink it a little bit. And so we have a bunch of output feature maps, and we're going to basically predict some bounding box, which is the size of kind of this filter that we were running over the image. And in this case, we'll probably output basically hopefully two bounding boxes that are roughly associated with the two people in this image. And one thing we have to think about is basically say that we've detected some objects, or sort of we think we detect some objects in the scene. How do we tell if we're right, and how do we kind of score or rank these object detectors relative to each other? So when we talk about scoring object detection, there are sort of these two things that we have to think about. We have to think about basically the bounding boxes that we're predicting, and also the classification that we're doing on top of those bounding boxes. So we have a bunch of bounding boxes, which are the locations of the objects, and then we also have predictions for what the class of those objects are. Is it a person? Is it a bicycle? Is it a dog, et cetera? So again, we have a bunch of classes, and we have a bunch of instances of those classes in the image, so we can't just use accuracy. So first we have to think about just like, what does it mean to get the bounding box correct? And in general, we talk about this metric called intersection over union. And intersection over union is pretty straightforward. Basically, we have some ground truth bounding box, which is like this green bounding box. And we have some bounding box that we predicted, which might be this red bounding box. And the idea is we're just going to take the intersection of these two bounding boxes and divide it by the union. So the intersection is obviously this blue region here, and we're going to just look at the area of that intersection. And the union is basically this purple region. And how sort of good we can think of prediction we have is given by taking the intersection of these two divided by the union. And it's pretty clear that basically if these bounding boxes don't overlap at all, the intersection is going to be 0. So the intersection of a union, or IOU, is going to be 0. If they overlap sort of perfectly, we're going to have the same value for the intersection and the union. And so the IOU will be 1. So the IOU is this number that varies somewhere between 0 and 1. And generally, people use different thresholds for what this cutoff should be for how good of an IOU do you need for a bounding box to be considered correct. 0.5 was the most common one for a really long time because the biggest data set that everyone sort of used 0.5. So that's typically what I think of as being like the correct intersection over union for whether or not you got a bounding box right. People have started to sort of push towards higher versions of IOU or also calculate metrics based on a varying IOU. So you can imagine calculating some metric based on an IOU of 0.5, but also calculating it based on an IOU of 0.75 or something else. So if you have like an IOU threshold of 0.75, that means that your bounding boxes have to fit a lot better toward the ground truth objects versus an IOU threshold of 0.5 or something like that. So do people sort of understand how we tell just if a bounding box is correct, sort of independent of what class we've assigned to that bounding box? Cool, so the next thing we have to do is basically figure out how well we classified all of these different bounding boxes that we've predicted. And to do that, we're going to use these two measures, recall and precision. And recall is, say you've predicted a bunch of bounding boxes. It's how many bounding boxes did you classify correctly based on how many total ground truth bounding boxes are there of that class. So say you predicted, say you correctly predicted 5 bounding boxes. So you predicted 5 bounding boxes that all had IOU of 0.5 or more with some ground truth bounding box, and they're all dogs. So you predicted a bunch of dog bounding boxes, and say you had 5 correct predictions, and say that the total number of ground truth bounding boxes for dogs was 10, then your recall is going to be 50% or 0.5 because you basically retrieved half of the actual ground truth bounding boxes that exist in your data set. So recall is this measure of basically, given all of these predictions, what percentage of the actual number did you sort of find? What number did you recall, I guess? Precision is this metric of how precise you are, how accurate you are with the ones that you predicted. So say that you predicted 10, again, say that you predicted 10 total bounding boxes, and 5 of them you got right. 5 of them actually have a dog in them, and your overlap was high enough, basically, and the other 5 you were wrong on, then you would have a 0.5 precision. So precision is basically the number of bounding boxes that you predict correctly, both in terms of overlap and in terms of what class you assign to them, divided by the total number of boxes that you predicted. So this is basically looking at all of your bounding box predictions and saying how good are you just in terms of predicting good bounding boxes. Or good bounding boxes and what class those bounding boxes are. So you can imagine that basically if you only predict sort of the bounding boxes that you're most confident in, if you're like, I'm 100% certain that there are dogs in these 5 bounding boxes, and you're probably going to be right if you just predict sort of the ones that you're most confident in and you have some model that's learning something. So you might predict basically very few bounding boxes, and you'd have a really high precision because you'd be really confident in all of those bounding boxes. But in your data set, maybe there's 1,000 dogs or something. You're going to have really low recall because all you found are 5 of the dogs that exist in your full data set. So you can imagine basically if you only predict your most confident predictions, you're going to have really high precision but really low recall. And as you sort of go down in terms of this confidence value for how confident you are in your predictions, you're going to predict more and more bounding boxes, and your precision is going to start to go down because you're going to start making some mistakes, but your recall is going to start going up. And so if you basically just kind of throw in all of the bounding box predictions that your model might make, regardless of kind of the level of confidence, you're going to have really low precision, but really high recall. So now we have these 3 things to think about, where sort of the correct bounding box is having an IOU over some threshold, And we assume that you also have some confidence that you predicted for what class of object is contained in this bounding box. Now we have recall and precision, which are sort of this trade-off between these two measures in terms of your model. So what we're going to do is basically plot this precision recall curve. And what this does is vary this threshold, or this confidence, and calculate a bunch of different points along sort of this different trade-off. So remember, at the beginning, we have really low recall but really high precision when we're only predicting sort of our most confident predictions. And then as we vary this threshold and basically add more and more predictions in, we're going to get some basically false positives, or we're going to miss some bounding boxes, et cetera. And our precision is going to start going down, but our recall is going to go up over time. And at some point, we'll sort of get down to the point where we're predicting so many objects, and there are only some number in the data set as a whole. Our precision sort of falls off precipitously, and our recall will sort of saturate at some amount too. Oftentimes, detectors nowadays get pretty close to 1. These are a bunch of basically versions of deformable parts models, the precision recall curves for deformable parts models. And so you can calculate basically average precision, which is the area underneath this precision recall curve. And this is how we're going to measure basically detection accuracy for a single class. So I think this is for person or something, I can't remember, or maybe like cow. And what we want, so average precision and sort of calculating the area under this precision recall curve is only for one individual class, basically. We can only do this calculation, or we're only going to do this calculation for each class individually. And then to measure the sort of performance of a detector, what we're going to do is basically calculate average precision for each of the classes independently, and then we're going to average them all together, and we come up with this metric, which is called mean average precision, which sounds like it might be redundant, but isn't actually, because it's the mean of a bunch of average precision calculations. And we can imagine basically varying what threshold of IOU we consider to be sort of a correct bounding box prediction. So before mean average, like originally, or sort of with the PASCAL data set, mean average precision always kind of referred to an IOU threshold of 0.5. But nowadays, people can vary this threshold. So you might talk about mean average precision at 0.5 or mean average precision at 0.75, or sort of these different thresholds for correctness in terms of these bounding box predictions. So I keep talking about PASCAL VOC. So we'll just actually talk about it a little bit. So this is one of the first really large detection data sets. It's not large in the same way that ImageNet is large, but it's large in terms of detection because it's really time intensive to go through and actually draw these bounding boxes on all of these objects in a bunch of images. So it is just 20 classes and 11,000 training images. There are 27,000 annotated objects, so there are a little bit more than 2 objects per image on average. And we're going to use this metric of mean average precision, and deformable parts models, which was kind of this pre-neural network thing that we talked about, has a mean average precision of 33.6, which isn't super high. All of these detectors have, I think that looks like about in the 30s in terms of average precision. Some of these might be a little bit lower. Some of them might be in the 20s. But 33.6 is doing something. If you just think about doing random predictions for classification, you will, if you have 10 classes, you're going to be right 10% of the time. So maybe your classification accuracy would be 10% if you just kind of predict random things. If you do that with detection, you basically get 0. You're almost never going to actually correctly predict things, just kind of randomly assigning some bounding box and some classification accuracy to random parts of an image. So doing 33.6 mean average precision is definitely doing some actual processing and getting some results on this data set. But now we've seen these huge gains of using neural networks on ImageNet for image classification. How can we kind of take these networks that do really well at classification and transition them over to performing detection. And we also sort of saw these networks doing segmentation as well. So there's this kind of fundamental problem with doing this transformation from classification to detection or segmentation to detection. And the problem that we have is basically this variable sized output. So if we're doing classification, our output is always going to be this vector. And we know how big the vector is. The vector is 1,000 classes, basically. And no matter what the image is that we're inputting, we're always going to be outputting a vector with 1,000 different probabilities in it that correspond to the different classes. The same is basically true of segmentation as well. So for segmentation, you have 20 classes or 40 classes or some number of classes. And the output is always going to be this static size where we're going to predict probabilities for each of these classes, and we're going to predict sort of this feature map that's the same size as the input image. So if your input image is 256 by 256 by 3, and we want to predict segmentation for 20 different classes, then your output is going to be a 256 by 256 by 20 image, and each of the channels of that image are going to associate with the probabilities for a given class in the image. Detection is different because we have this variable number of outputs that could exist for every image. So an image might not have any objects in it, in which case you don't want to predict any bounding boxes or any classification probabilities. And an image can have sort of an unbounded number of objects in it. So it might have 10 objects, it might have 20 objects, et cetera. And so for some images, you basically want to predict like a couple bounding boxes. For some, you want to predict 10 bounding boxes or 20 bounding boxes, et cetera. And you have basically this unbounded upper end where you could basically have an image that has sort of arbitrarily many objects in it, and you want to predict some bounding boxes for each of those objects. You also, so it's kind of hard to basically map this problem of object detection onto these neural networks, because with a neural network to sort of train it, you have to have basically a fixed size output so that you can calculate some loss at that output and backpropagate it, et cetera. So the first sort of foray into doing this, or first sort of attempt of doing object detection using some form of neural networks was this algorithm called RCNN. And this is regions with CNN features. And this is actually by the same guy who did deformable parts models back a couple slides or whatever. So this guy, Ross Gershik, who was very involved in doing deformable parts models, then basically afterward came up with RCNN, which starts to add in some of these neural network things that we were thinking about before, but using them to perform object detection. So deformable parts models is an example of this sliding window approach where we have these filters and we're going to apply them to basically every spot in the image. And you can imagine doing that with neural networks as well. So you could imagine basically taking a neural network and running it basically on every window in an image and producing some classification score, and then figuring out where the high scoring regions of an image were and basically detecting things at those areas. But the difference between sort of running the deformable parts model sliding window, which was this really simple SVM classifier, and running a convolutional network is that convolutional networks are really slow. We have a bunch of different layers. It takes a long time to do all of these convolution operations, et cetera. So deformable parts models, I think, looks at on the order of like 100,000 or hundreds of thousands of sub-windows in every image. And if you have to run a neural network like 100,000 times to produce object detection results for an image, that'll take sort of an unbounded amount of time. It'll take a really long time. So we don't want to do sort of this sliding window approach. And the idea with RCNN is basically first what we're going to do is extract some region proposals. So instead of basically looking at every sub-window or every possible thing in the image that might be an object, first we're going to extract a bunch of rectangles, a bunch of bounding boxes that might have something in them. And then we're going to basically take the image components of just these bounding boxes, resize them to fit sort of this neural network that we have, run them through the neural network, and use that to classify, is this a person, is this a dog, is this a cat, or is there just nothing here? Maybe it's just like background. And sort of if all of these classification probabilities end up being no, then we know that there's just no object associated with this region, and we can throw it out completely. So instead of doing sliding window detection, we're going to do this basically region proposal-based method. And the first question is basically, how do we actually get all of these different regions? And the way we're going to do this is selective search. And what selective search is doing is basically producing successive segmentations of the image, superpixel segmentations of the image, and drawing bounding boxes around those superpixels. So what superpixel segmentation is doing is just looking at kind of nearby groups of pixels that look similar to each other. And we talked about some similar concepts when we talked about k-means clustering of an image based on the color. You can basically, without doing any like really advanced or like intensive processing, you can basically separate out different colors of an image that are similar to each other. And what we're doing here is very similar. So you sort of just pick a pixel in the input, and you look at nearby pixels in the image. And if those pixels are very similar in color, or sort of, they're within some distance in terms of the color of the original pixel, you're going to add them all into the same group. And you're going to sort of expand outward until you find some region of pixels that is far enough different that you don't add them into your group. And then you're going to start making another group, et cetera. So what selective search is doing is basically building up a bunch of versions of this segmentation mask of the image. And the first version is just really low threshold for what pixels are related to each other versus what pixels are in different groups. So we get a bunch of different groups in this image that are all sort of considered to be pixels that are different from each other. So we see that the sky is pretty uniform in color, so all of those pixels are kind of the same, and they all get added into the same group. Versus, down near these sheep's legs, we have a bunch of variation in color, and we have a bunch of like little segmentation groups, sort of little superpixels that all end up forming. And what we're going to do is basically take this segmentation mask, and around each of these groups of superpixels, we're just going to put a box. So we have this big green region up here, and there's sort of a corresponding blue box in the selective search output here. We have, the little person's head is one little superpixel that's these blue pixels, and there's a box that corresponds to that person's head, et cetera. So we're going to take all of these sort of discovered superpixels with some really low threshold, and we're going to put bounding boxes around all of those things. Then we're going to increase our threshold a little bit and basically start merging together these superpixel predictions into slightly larger groups. We're going to put bounding boxes around all of these things and get sort of these coarser and coarser segmentation masks and put boxes around all of the different groups that might exist that we sort of discover by doing this process. And at the end, basically, we have a bunch of different regions in the image that we think sort of might be coherent objects in some capacity. And the idea basically is like if you have an object like this sheep or something, all of those pixels sort of look similar to each other, and all of the pixels in the background hopefully look a little bit different, or at least hopefully there's like some border. Like you can see in between these sheep, there's this like border of green in the background. So the idea is that at some point in this segmentation process, all of the pixels associated with this sheep are going to be in the same group, and we're going to draw some bounding box around that sheep. And that will sort of occur for all of the objects that exist in this image. And so at some point, we'll kind of produce bounding boxes that correspond to all of the objects in the image. We produce, obviously, a ton of bounding boxes. So a lot of these are going to be background. A lot of these aren't going to contain objects. So we just have a bunch of bounding box proposals. And this is basically better than doing sliding window because we're ignoring a large portion of the image. For example, we're not going to slide a window over this large region of sky because we know that if there is some object here, all of these pixels are very similar to each other, so it would be really hard to sort of discover like some little object hidden in there. And it's probably just the case that all of those pixels are just kind of background pixels, and we don't have to sort of look into that too much. So doing this, we basically can extract far fewer bounding boxes than doing sliding window detection. And now we can actually basically run our convolutional neural network on each of these extracted regions. So instead of doing sliding window where we would have like 100,000 or more different regions to run through our network, now we only have about 2,000 per image to run through our network. And we can just basically take each of these regions, resize the image that exists in those bounding boxes, run it through a network, and we get some predictions that correspond to, was this a dog, was this a person, et cetera. And this is, in some ways pretty similar to kind of the old way of doing computer vision, where we have kind of this long pipeline of like, we have this input image, we're going to extract these region proposals, we're going to look at each of these regions and sort of classify them into person or dog or cat or whatever. And in practice, there are sort of more steps in this pipeline. An added sort of component is that we have this region and we're going to predict what class it is, but we could also imagine basically selective search isn't going to produce perfect bounding boxes, so we could add in an extra prediction at this prediction phase that computes basically how much should we shift the bounding box to be a little bit better bounding box around what the object actually is in the image. So we basically are going to predict basically small changes in the center coordinate of the bounding box and also in the height and the width. Remember, in the past, we've basically done non-max suppression. We think that we might basically produce a bunch of duplicate predictions for the same thing. We're going to do that with object detection as well. So a lot of times we'll have a bunch of bounding boxes that all have some overlap with some ground truth thing. And each of those bounding boxes is, so for example, in the sheep picture, we have a bunch of bounding boxes that are around, this sheep, for example, or sort of correspond to parts of that sheep or have some of that sheep in it. So we're going to have a bunch of overlapping bounding boxes, and we want to figure out which one the best one is. So we do non-max suppression, where basically we look at overlapping bounding boxes, find the one with the highest confidence, and then if that high confidence one overlaps by the other bounding box predictions by some amount, we're going to basically downweight the other bounding box predictions, so we only are left with this high confidence prediction at the end. There's also a bunch of things that people have sort of added on top of our CNN to do some post-processing, things about reasoning basically between different objects in an image. So if you see a dog in an image, maybe that makes it more or less likely to see a person or a bicycle or something like that. And you can basically do some kind of reasoning. So remember that all of this reasoning that we're doing up here is independent. So when it's processing whether or not this is a person, this evaluation through the neural network is totally independent of processing whether or not this bounding box is a horse versus whether this bounding box down here is a sheep or something. Each of those passes are independent, and we get a bunch of bounding boxes that have some class prediction, but maybe we can use some extra reasoning on top to find relationships between different objects that might co-occur or might not co-occur in a scene. So there are a bunch of kind of steps of post-processing that people have added on to this. But the result are basically really good. So remember before, the deformable parts models had somewhere in the 30s in terms of mean average precision. When we do our CNN with different architectures for what this CNN classifier is, if we use AlexNet, we get 53.3 mean average precision. And if we use VGG, we get 62.4 mean average precision. So this is like a doubling in terms of this metric, this mean average precision, for how good these object detectors are. But again, this is like this really slow process that takes a long time. It takes like 20 seconds per image to process one of these images using our CNN. And this is on like a GPU, so this is on something that already is like 100 times faster than a CPU. This was on a K40 back then, I think, or a K20 maybe. So a really high-end GPU. It still takes a really long time because basically we have to run all of these images through this neural network independently, and we're not running this neural network 100,000 times, but we're still running it like 2,000 times, and that takes a long time. So this was the phase when I started grad school and started working on this algorithm called YOLO, which stands for you only look once. And the idea was basically, in the past, you had to basically look at this image like thousands of times to extract some detections for that image. And that seems kind of crazy. Like, why are we running this neural network like 2,000 times to process this image? Maybe we should just run the neural network once and calculate all of the detections for the image. And so to start with, we're just going to kind of try it out and see what happens. So this is something that you guys can kind of play around with at home as well. But it's fairly easy to get working. And especially if you've kind of gotten the homeworks to work on your computer, there aren't any more dependencies in this. So this should work kind of equally well. So we can just, I want to make a new directory so you guys know I'm not cheating. So we're going to clone the directory from GitHub. We're going to change directory into it. We're going to make the project. And then we have to get some weights for, so we'll just run basically a pre-trained network. And these are all kind of the large version of it. But there is basically a small version of the weights that you can download as well to do basically a slimmed down version of the model. So the large version of the model will run pretty quickly on GPU, but takes a pretty long time on CPU. This version will run in about a little bit under a second on CPU. And so if we run it, well, something happened. We don't really know what. We ran it on this image, dog.jpg. And so if we open the folder that this is in, hopefully we have some predictions. And it looks like we found basically the dog and the bicycle. And it can't really tell if this is like a car or a truck, but it's still doing something. So that's pretty cool. We can also, again, just like in your homework, we can make OpenCV available and recompile. And I already have OpenCV installed, but we just get a ton of random warnings from OpenCV. I don't know what it's all thinking here. That will at some point finish. And then we can run it and have sort of input different images. Oh, this is displaying on my screen. This was the image that we displayed for that. And we can sort of look in here. I give you a bunch of images to kind of play around with originally. So there's eagle and giraffe. So if we do eagle.jpg, hopefully it finds a bird. Oh, it's moved it over to my side again. And if we do giraffe, hopefully there's a giraffe. It also finds a little zebra in the image as well. And the same way that we can sort of run that homework that you guys did on your webcam, we can do the same thing here. To remember how to invoke all these things. It works. Over here again. Hey, look at that. And again, this is all running on the, if it can't see my face, I don't think it thinks I'm a person. This is all running on the CPU of my machine, so it's like a lot slower than it would be if it were running on a GPU. It's also this like much more slimmed down model. So it isn't as accurate. It also just is sort of dark in here, so it can't totally figure out what's going on. But hopefully it does some kind of level of accuracy and is a little bit more usable in terms of running on CPU and stuff. So this is something that you guys can go play around with, especially for like final projects and stuff. Just a resource that's out there in terms of detection that is a lot faster than our CNN. And next time, we'll talk about how it works But that's all I have for right now. So go crazy.